Can you see my screen? Is the screen
Yes,
visible?
sir. Yes, sir. Yes, sir.
Okay, fine. Okay, so so today, before we start talking about anything technical, let us look at a fun question. So suppose I have given you a matrix A. Okay, let's say it's a 2 cross 2 matrix. So 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 let's say this is the matrix which has been given to you. Say this is the matrix that has been given to you. Now you have been asked a question like what is the and this is like this element is missing. Okay, so now you have been asked that tell me what this element is. So if this is the question that has been given to you, obviously you will not be able to say anything. I mean, this can be anything, right? It can be 1, it can be 2, it can be 7, it can be 29, it can be minus 3.5, it can be 1,50,000. Anything is possible. We have no information about this. Okay, so like if someone gives you this kind of an incomplete matrix and asks you to put in the value here, then you will not be able to say any, like you won't be able to say anything. Now but still I want to make some kind of an estimate about this missing element. Now so clearly I will be able to say something only if I have some more information about the matrix. So can you suggest some information about the matrix which will enable me to answer this question, what is the remaining element?
Sir, determinant of the matrix.
Determinant of the matrix, that's a good idea. Yes, if you like if you know the determinant of the matrix, then you'll probably be able to basically solve an equation and yes, and get the remaining value. Anything else apart from any other thing apart from determinant?
Trace.
Trace. Okay, fine. What about rank? If I tell you that this matrix has, so okay, so so first of all, what is the max like what do you think is the rank of this matrix? What can be possible values of rank of this matrix?
1 and 2.
It can be either 1 or 2, right? Obviously it cannot be anything like it obviously it cannot be 3 or anything. So if it is 2, then can you can you answer what is this value going to be?
For 2, there will be a lot of possible values.
A lot of, as in?
If we want rank 1, then there is only one solution.
Correct. And
If
what
we
is that
want
solution? If it
3,
is rank 1, then the solution is 3. Right.
and
So
then
if it is rank 2, then it can be anything, right? There is no absolutely no restriction. Right. So if I know that the rank of this matrix is 1, then I will be able to uniquely determine the solution to this question. Now let us consider a bigger matrix. Suppose you are given this matrix. Okay. Now that is of course by looking at the pattern of the numbers, you have probably already guessed what what the remaining elements are going to be. But so let us see which all things help us to, or which all properties of the matrix help us to find out what the remaining values are. So so some of the things that you already mentioned are trace and determinant, right? So if we know the trace of this matrix, then does it help you to find out the remaining elements? Then no, because the trace is like basically the sum of the diagonal elements. We know all of them already. The trace does not like all the missing values are the off diagonal, so the trace will not help us. What about determinant? Like can we find the remaining values, the missing values, if we know the determinant of this matrix? Yes, no?
Not.
Sorry, I could not hear. There's a lot of noise. Yes or no? Can we find, if we know the determinant of this matrix, can we find the remaining elements?
No, sir.
Oh no.
Because there are lots of possibilities, right? That is, if we keep write x1, x2, x3, x4, etc. So basically we will get a single equation with lots of unknowns. So we'll probably not be able to solve it. So like in this case, trace, because it was a small matrix, trace or determinant could have helped you. In this case, it still does not. Now suppose I tell you the rank of the matrix. So suppose again, if I tell you that the rank of the matrix is 4, that is of course it cannot be anything more than 4. So if I tell you that the rank of the matrix is 4, then will you be able to solve it? Obviously not, because like rank 4 matrix, if this is a full rank matrix, means basically these values can be anything. On the other hand, if I tell you the rank of this matrix is 1, then what? Then can you say something about these missing elements? Yes.
Yes, sir.
Yes.
So what are the missing elements going to be if it is rank 1? What is this element?
4.
For this one?
2.
Yeah. So you have got it basically. So let's not waste time in how you got the thing, or what, it becomes pretty obvious. So basically this suggests to us that if a matrix is has low rank, then it is possible to solve this problem of missing elements. Low rank means what? That is of course it can, these matrix can have rank 1, 2, 3 and 4. We have seen in case of 4 we cannot solve it. In case it is 1, then we can solve it completely. Now we may be tempted to ask, what about ranks 2 and 3? If the matrix had rank 2, then would you have been then like would we have been able to solve it or not? So I will leave it to you as an exercise to brainstorm. What would have, if I had told you that this matrix has rank 2, then would you have been able to solve this problem? So so it turns out that this is actually a quite significant research topic. This is known as low rank matrix completion. That is, we are given a matrix which we need to, an incomplete matrix which we need to complete, and the thing is so if we do not know anything about the matrix, obviously I will not be able to complete it. But if I know that the matrix has low rank, then I may be able to solve it. If the matrix has especially if I know that the matrix has rank 1, then I may be able to solve it exactly. If like if it has some small rank which need not be 1, then also under certain conditions I may be able to solve it approximately. That is to say, I may be able to get or I may be able to find some approximate solutions to the missing values. So this is the low rank matrix completion problem. Now so why is this important? So this problem, it is actually quite important in various applications of machine learning. So most importantly, it is important in the Netflix challenge problem or the Netflix ratings challenge problems. So what is the Netflix ratings problem? The problem is as follows. So we have basically there are M users where M is like or rather let us say that there are M number of movies where M is some large number, let's say 1000 or something like that, and N is users. That is, there are a very large number of users, maybe 1 million or something like that, and the elements of the matrix are basically the ratings given by the users to the different movies. So for example, if I am so let me denote this matrix by X. So if I say X I comma J, okay, if I say X I comma J is equal to 3. So let us assume that all the users can give ratings 1, 2, 3, 4, 5 to every movie or to any movie which they want to rate. Of course, not all users will have watched all the movies, and even if they have watched, they may not have given a ratings. So basically, this will be a very sparse matrix. Only a small number of these ratings will actually be known. Now, if I say that Xij is equal to 3, that means that the ith user has given a rating of 3 to the jth movie. Okay. So as I said, this is a very sparse matrix. Most of these elements are not known to us. Now the question is, if I want, let us say, for example, that this is 3. Let us say maybe this entry is 5, or this entry here is 1, etc., etc. So if this is the situation, then the problem is as follows. Basically, the problem is complete this full matrix. That is to say, predict what rating the there is a mistake here. This should be movie, and this is the user. So the problem here is as follows. Basically, the problem is to complete the matrix, which also means that for any arbitrary user A and movie B, predict what rating that user A would have given to the movie B. Okay, this is the Netflix ratings challenge problem. So obviously, as you can understand clearly, that this is a matrix completion problem. This problem is directly relatable to this problem. So so obviously there is no, like, there cannot be any unique solution to this problem, and like if we do not know anything about this matrix or anything about the users, then I will not be able to like give any ratings to the problem. I won't be able to give any meaningful solution to the problem. That is to say, all solutions will appear equally likely. There is, even if there is a ground truth which is not known to me, then also there is no possible way in which I can fill up this matrix. Now let us see if low rank helps this problem or not. So that is to say, we have already discussed that if I know that this matrix is low rank, then I may be able to solve this problem in a somewhat reasonable way. What do I mean by somewhat reasonable way? What I mean is, let us say that there is an actual ground truth matrix x0, x0. Okay, that is not revealed to me. That is, this is x0 basically is the complete matrix. So suppose I had actually forced all the users to give ratings to all the movies. I mean, not random ratings, but honest ratings. Then if the matrix which I would have got, let it be x0. Of course, it's a different matter that in this case I do not know what is x0. But there are results which say that if rank x0 is less than equal to some value k, then I will be able to find an x hat. Okay, what is x hat? Is some is basically some matrix of same size, m cross n, such that x hat minus x naught, its Frobenius norm, is less than some value epsilon, which is, and this epsilon depends on k, and x hat omega is equal to x of omega. What is omega? Omega is the set of revealed entries. So like most of the elements of this matrix are missing or hidden. So, like some of the, only a small number of them are visible or revealed. So let those entries which are available, including their positions, I mean not their values but their positions, let the set of such locations be omega. Okay, so what am I saying, or like what are the theoreticians saying? The theoreticians are telling me that if the actual matrix x naught, right, the true matrix x naught which has not been revealed to me, if its rank is below a particular value k, now I do not know what this k is, but any k, if the true matrix has rank less than equal to k, then I will be able to find x hat by some algorithm which will be which will be quite close to the original matrix or the true matrix x naught. And what I mean by being close is the difference between the Frobenius norm of their difference is going to be less than a certain quantity. The Frobenius norm of this difference matrix is going to be bounded by a quantity. And furthermore, x hat omega is equal to x omega. What is x omega? X omega is basically the set of the revealed entities. So we can say that x omega is equal to x naught omega, right? X omega equal to what is x? X is the matrix that is revealed, that is actually provided to us. What is omega? Omega is the list of the locations where I actually have access to the ratings. And what is x naught? X naught is the true full matrix. X naught is the true full matrix or true complete matrix. So this statement that x omega is equal to x naught omega is basically telling me that those locations where I have access to the readings I can see are actually equal to the true ratings. That is, it is not that there is any measurement error. It is not that this rating, this first user has given a rating of 2 to the second movie, but I have erroneously reading it as 5. No, that is not happening. If this is 5, if in the X matrix the 1, 2 element is 5, that means the first user has actually given the rating of 5 to the second movie. So that is what is indicated by this condition. And what is this condition saying? What is x naught? This is the estimated full matrix. Fine. So I do not, so x naught is what it is supposed to be, x hat is what has been estimated. Estimated how? Estimated by some algorithm which we will not study in this class. But let us say that there is an algorithm based on optimization which is there. So what is the theoretical result saying? Theoretical result is saying that the estimated matrix x hat will be close enough to the true matrix x naught in terms of Frobenius norm. How close? How close is that depends on the rank x naught. If the rank of x naught is quite high, then like the Frobenius norm of this difference can also be quite high. That means I will not be able to estimate them correct, like very well. But if this rank is of x naught is quite low, maybe 1 or 2, then I can say that then this quantity will also be quite small. Which means that the estimated matrix X hat will be quite close to the original matrix X naught. That's what this result is telling us. Okay. So, so this is like quite hypothetical. This can become useful if I can say that there is any reason for me to believe that X naught is actually low rank. That is, if I can actually bound the rank of matrix X naught. So, so this is the user rating the user rating matrix. Now, why would I think that this matrix is low rank, right? In this case, I did not that is, I told you that this matrix has rank 1, then only you are able to solve it. In this case also the same thing. So here, of course, why will I think that, or what is the reason to think that this matrix will be low rank? So can any of you suggest why this user movie rating matrix may be considered to be low rank? Can there be some vague rationale for thinking that this is a low rank matrix?
Sir, because
The
many users can have same ratings called rows.
Right. And why so? Why can many users have same ratings?
They
Or
might have same taste.
exactly. So different users may have similar tastes, and similarly different movies can also be similar in some sense. So an user who gives high, it's like suppose two users have similar tastes, then it is likely that they would have given similar ratings to to any set of movies. On the other hand, consider two movies which are quite similar to each other. In that case, it's possible that all the users will give approximately similar ratings to that movie, right? So based on this, of course, this I am not guaranteeing that it will be perfect. That is, like that users will have exactly the same taste. That is to say, we cannot say that if one user has given ratings like 1, 2, 3, 3, 2 to the different to 5 different movies, the other users will give exactly the same ratings. But we can say that maybe their ratings will not be very different. Maybe instead of this particular thing, maybe they would give 2 to 3 to 1. This kind of rating also they may give. But but there is some reason to think that and if I can approximate this matrix by I mean, if this matrix X naught, if I can approximate it by a low rank matrix, that approximation will not be very bad. Okay. So so then basically the question is, how can I approximate any given matrix by a low rank matrix? That is, what I am trying to say here is that X naught may not be a low rank matrix, but X naught may be quite close to a low rank matrix. That is, instead of satisfying this particular condition, if I let me satisfy another condition. What's the other condition? The other condition is that there exists a matrix X1 such that rank of X1 is low. I am not specifying how low. Let me just say it is K, where K is quite low compared to the size of this matrix. The size of this matrix is M cross N, where M is small and N is large. M is not very small. It's still, even though it is smaller than N, it's still quite large. But so the rank of this matrix X naught, that is to say rank of X naught, obviously this will have to be less than or equal to M, right? Since N is greater than M, this rank of X naught can never be more than M. It can be at most M. Now I am saying that there is another matrix X1 whose rank is K, where k is much less than m. Okay, that is to say k is quite low compared to m. Furthermore, x1 and x0 are quite close to each other in terms of Frobenius norm. Okay? That is to say there is a small quantity delta such which bounds the Frobenius norm of the difference between x1 and x0. Fine. That this basically means what? This basically means x0 can be approximated by low rank matrix x1. Okay. So if x0 can be approximated by the low rank matrix x1 and this delta is basically the error of approximation, then I can I can move or I can actually make a corollary to this result. So here this result is true for those x0s which have low rank. Here I am saying those ranks, those matrices which are close to a low rank matrix. So then basically I know that instead of x0, in this case what I was trying to do is I was trying to estimate x hat which is like x0 itself. So here I will not try to estimate x0, but instead I will try to estimate x1, and that I will be able to do reasonably well using these with the help of these whatever small number of entries have been given to me. And further I know that the x1, that is to say what I will get is x hat. This x hat, I know that this x hat is going to be quite close to x1 because x1 is low rank. And furthermore I know that x1 is quite low, close to x0. So then I will be able, basically I have these two relations. Relation number one is that x hat, the matrix which I have estimated, that is quite close to x1, x1 being the low rank matrix. And the second information I have is that x1 is quite close to x0, right, where x0 is the true full matrix, right? So now since I have got these two relations, where I mean in both cases I am talking about the Frobenius norm. Now since Frobenius norm is a norm and I have got these two relations, I can apply what the famous triangle inequality, which will enable me to say that. So what is the triangle inequality saying? The triangle inequality is saying that x1 minus, sorry, x hat minus x1 Frobenius norm plus x1 minus x0 Frobenius norm. So what follows after this according to the triangle inequality? What should I write after this?
This is less than equal to x hat minus x1 Frobenius norm.
Less than equal to, is it less than equal to?
Greater than equal to x hat minus x0 Frobenius norm.
Greater than the sum of these things, which is x hat minus x0 Frobenius norm. Fine. So I know that this thing is greater than equal to what? Greater than equal to epsilon k. And this thing I know is greater than equal to delta. So basically I can now say that using these two things, what I can say? I can say that.
So why is greater than or equal?
Less than equal.
Sir, it is less than delta and this thing.
Sorry.
1 and 2 is.
Sorry. Yeah, right. So this is less than equal to. right? So these like so basically I know that this thing is less than equal to epsilon, this thing is less than equal to delta, so I can just add up and I know that this sum is then less than equal to delta plus epsilon k, right? But this sum is greater than equal to this quantity. So using the triangle inequality, what I get is x hat minus x naught Frobenius norm is less than equal to delta plus epsilon k. Correct? That means what? That means I have been able that although x naught is not actually a low rank matrix, but it is actually quite close to a low rank matrix x naught, and I mean close in terms of Frobenius norm. And if that is the case, then using some algorithm which exists but which I have not mentioned to you, using that algorithm I will be actually be able to estimate x hat, which is again quite close to x naught, right? This is the result that that I am stating without proof. So this is this algorithm. I mean, there are lots of algorithms which have emerged since the past 10 or 12 years. The first result was given by Candace et al. In 2009. So this Professor Candace, he is a professor of Stanford University. So he gave the first algorithm to estimate x hat. So using this algorithm we can like basically estimate the missing values of a low rank matrix. And if a matrix is not actually low rank but it is quite close to a low rank matrix like this, then also the same algorithm can be obtained to I mean the same algorithm can be used to obtain a matrix x hat which is close enough to the original matrix x naught. Okay. So all this is fine. So all this like this all this is an active area of research which has been motivated by this Netflix ratings problem, but of course it has many other applications also. But the important thing here is the most important concept here is this low rank approximation. Why is that important? Because not many matrices are actually low rank, but it may be possible to approximate them quite well by a low rank matrix, right? So like an example of this we actually discussed just now. So like we discussed that because of the user's tastes, etc., this Netflix matrix will it may be possible, it's not impossible to consider this as a low rank matrix. Of course this will not, even if two users have exactly the same taste, then also they are not going to give exactly the same ratings to all the movies. There will be small difference. So but the rank is such a thing that even if there is a small difference, that rank may be spoiled. Say for example, if you consider this matrix 4263, this matrix has rank 1 obviously, but even if I change this slightly, even if I perturb this 3 to say 4, or if I perturb this 6 to 7, right, it's no longer it's no longer a rank 1 matrix, it has become a rank 2 matrix, even though it is actually quite close in terms of Frobenius norm or in terms of the magnitudes of the elements. This is quite close to the original matrix 4263, that is rank 1 matrix, but it is not a rank 1 matrix. So similarly, this Netflix ratings matrix x naught, this cannot be, or we cannot expect that this will itself be a low rank matrix, but we can expect that there will be a low rank matrix x1 which will be quite close to it in terms of Frobenius norm, and that x1 is what we are estimating here. Fine. So then the question arises, how do I, like given any matrix x or x naught if you want to call it, how do I find an x1 which is which is quite close to x naught but it's also low rank? So basically what I am trying to do is I am trying to find a low rank approximation of x naught. That's basically what I am trying to do. So I want two things. That is like when I am talking about x1, x1 should have two properties. One is that it should have low rank, that is the rank of x1 should be as low as possible. That is, in other words, it should be bounded by some value k. And secondly, x1 should be as close to x0 as possible. That is to say, the Frobenius norm of their difference should be bounded by some value delta. Okay, so I want to find such an x1 for which k and that is for that is given any small k and delta. I want to find x1 for which both these conditions are simultaneously satisfied. Okay, this is what I want to do. Now, so what is so you may be wondering that why I am telling all these things. So till yesterday we were talking about singular value decomposition or SVD. So what has this got to do with SVD? So it turns out that this has got a lot to do with SVD. So if you remember, yesterday we wrote down x as in this way: I equal to 1 through r sigma I ui vi transpose, where what is sigma I? Sigma I is the ith singular value of x. What is vi? Vi is the ith right singular vector of x. And what is ui? Ui is the ith left singular vector of x. Fine. So in fact we had written down this relation also, that ui is actually nothing but 1 by sigma I times x into vi, right? This we have all discussed in the last two classes. And what is r? R is nothing but rank of x. Okay, so x is, as we had discussed earlier also, x is an m cross n matrix. So r, whatever that r is, it will have to be less than equal to min of m comma n. It can, like, if I do not know whether m is larger or n is larger, but whatever it is, r cannot be larger than the minimum of them. If m is less than equal to n, then r can be at most m. It can be lesser also. So now the question is how let us say that this is how I am able to express x in this form. Now the question is, suppose I want to get the low rank approximation of this matrix x. That is to say, x has rank r, but I want to get a matrix x1 which will satisfy these two properties. That is, its rank will not be more than k, and it will also be as close, that is, its Frobenius norm of its difference from x will also be as close to I mean, it should be bounded by this quantity delta. Okay, instead of x, let me write it as x naught for the uniformity of notation, right? So now, if the claim is that I can define x1 in the following way. So remember that k here is strictly less than r. R is the rank of the full matrix x naught, and I want the matrix x1 whose rank will be at most k, where k is significantly less than r. I can actually write much less than r. Then only the low rank approximation will make sense. Okay, So now the question is how to get, from where do I get this x1? And my claim is I can write x1 if I define x1 as I equal to 1 through k sigma I ui vi transpose. Okay, if I define x1 in this way, using the same sigma, same u, same v as x naught, right? I had got the that is I had got sigma 1, sigma 2, etc. as the singular values of x naught. Similarly, v1, v2, u1, u2, those also I had got from x naught. I am using the same singular values, etc. But instead of going all the way up to r, I am just stopping at k. Okay, that way I am getting and using that that is to say using the first k singular vectors and singular values of this matrix x naught, I am constructing x1. Okay, so this x1, as you can see, understand, this is basically a rank deficient version of x naught, right? And as you can understand, the rank of this x1 in this case is obviously is equal to k. Rank x1 is equal to k. Just like when I added up all these things up to r, then I got an x naught whose rank is r. Similarly, if I keep on adding these matrices only up to k, then I will get x1 whose rank is k. Okay. Now the question, so basically what I have done is, what is x naught minus f x1? So from this definition, what is x naught minus x1? Can you tell? How can I write x naught minus x1? Yes, the definitions are right in front of you. This is the definition of x naught, and this is the definition of x1. Right? So so obviously x naught minus x1 should be equal to I equal to k plus 1 till r sigma I ui vi transpose. Right? Now I am interested to put a bound on this the Frobenius norm of this difference. That is to say, I want this to be delta. So what is this thing? X naught minus x1 Frobenius norm. This Frobenius norm is going to be nothing but the Frobenius norm of this matrix, right? Fine. Now, this thing, if you consider this quantity, obviously this is also a matrix. And if you consider like these same things are actually the singular values and singular vectors of this new matrix, which I am calling as x naught minus x1. I can give it some other name also. I can call it as, let's say, x2. So x2, for x2 matrix, these will continue to be the singular vectors and singular values, right? And this then what happens to the Frobenius norm of x naught minus x1? This Frobenius norm is then, sorry, I equal to k plus 1 through r, this thing. Right? Now, if you remember, yesterday we had discussed one result that given any matrix A, what is its Frobenius norm equal to in terms of its singular values? So do you remember what that result was? If any matrix A, if it can be written as U sigma V transpose, then the Frobenius norm of A is equal to what?
Root under of sum of squares of its singular values.
Right, right. So basically, in other words, we can also say that this is nothing but the, like suppose all the singular values I just arrange in the in form of a vector. So this is nothing but the L2 norm of the singular values, right? So instead of writing it as a like as a matrix, if I write it as a vector of the values, then this is, which is also same as the matrix also. So basically it's nothing but the Frobenius norm of this this sigma, which is also equal to the L2 norm of the like the of the singular vector. I mean sorry, the vector of singular values. So basically now if you consider this matrix, the remaining singular values of x naught, which is say sigma k plus 1, sigma k plus 2, etc., all the way up to sigma r, those are the singular values of this matrix. So the Frobenius norm of this matrix is nothing but just the remaining singular values of this thing, which is nothing but L2 r sigma square whole to the power, sorry, not I equal k equal to 1 whole to the power half. Fine. So now if these singular value, like if all of these singular values are quite close, sorry, I mean quite small, that is to say if these things is less than equal to delta, then yes, I have got x1 which is close enough to delta. Right now, whether the single, like of course, that is, I do not know what these, like what exactly these singular values are. So given any delta, I cannot say that like whether the sum of these remaining singular values are going to be smaller than delta or not. If so, then yes, I can get a low rank approximation x1 of x naught. If not, then I will not get that this particular low rank approximation. That is to say, like like this delta, if I am satisfied, like if I am supplying from outside, then I may not be able to find that. Then the question is, will I be able to find x1 which satisfies this criteria? So the answer to that depends on the singular values of x naught. If the high singular values, that is if the singular values from k plus 1 to r, if those singular values are small enough that their L2 norm is less than delta, then yes, then I will be able to get it. If they are not, if the if the low singular values are quite large, then I may not be able to get it. Okay, so whether, so for every matrix x naught, I can always get a low rank approximation. Given any value k, I can always find its approximation x1, which is as close to sorry, whose rank is k now, and its the difference of its Frobenius norm from the original matrix x naught is bounded by this quantity. Now, whether it is also going to be bounded by the tolerance value delta which you have supplied, that depends on these quantities. It may happen, may be satisfied for some quantities, may not be satisfied I mean, for some matrices it will be satisfied, for some matrices it will not be satisfied. Depends entirely on what matrix has been given to you. Fine, but I can, there is a result which says that the matrix which you get in this way, this is the best possible approximation you can, or low rank approximation you can get for this x naught. In other words, x naught minus x1 Frobenius norm square is less than equal to x naught minus b Frobenius norm square, where rank b is r. Right, where B is any arbitrary rank R matrix. So it's basically saying that whatever, that is, x1 is the best matrix of rank R which approximates x naught. If you take any other rank R matrix, the approximation which you will get with respect to x naught cannot be any better than the approximation which you have got in this particular way. Okay, so basically the concept of SVD or yes, anyone had a doubt? So basically what this tells you is that using the concept of SVD, you can get a low rank approximation of any matrix in this way, and that approximation will be better than will be as good as possible. That is, you will not be able to find any other matrix of the same rank R which gives a better approximation than what you have already got. Okay, that's the result.
Sir, can you repeat what B is?
B is any low rank matrix of rank R. Sorry, any matrix of rank R. Well, I mean, of course, B will have to be have to have the same size. So if X naught has size m cross n, B will also have to have the same m cross n. So B is any arbitrary rank R matrix of the same size. And so
Sir,
what is, yes?
Sir, B is of rank R or rank K?
Sorry, rank K. I'm sorry. Yes, rank K. Thanks for pointing out. Rank K. Sorry, R is the original rank of the matrix X naught. X1 is rank K matrix. So basically what I am trying to say is that X1 is a rank K matrix. If I now the thing is that X1 is the best rank K matrix which can approximate X naught. If you find any other matrix B which has the rank of K, then you will never you will not be able to do any better than X1 in terms of approximating X naught. So this is one important application of SVD. Now let us consider one more important application of SVD. Before that,
Sir, in this we don't know x naught.
X naught is given to us. We know X naught. I mean, in the matrix completion problem, in the Netflix challenge problem, we do not know X naught. But what I am trying to say is that if X naught was known, then we would have been able to get a low rank approximation of that. I am not making use of that assumption for solving the Netflix problem. In case of the Netflix challenge problem, we do not need to know X naught. It is enough if we know that X naught is close enough to a low rank matrix X1. So now having discussed, so this is one important, so basically here we are using the concept of SVD to make low rank approximations to matrices. That is, if you are given a matrix and you want to find a low rank matrix which is quite close to the original matrix, then this is one way which you can do it, that is by which you can find that low rank approximation. This is one important application of SVD. Now let us come to another important application of SVD. Before that, let us study one important property. So let us say that X is any m cross n matrix. So X, as we know, we can write it in this way by SVD. Now you may be interested to ask what about the inverse of X? So obviously we know that if M if it's not a square matrix, then I will not be able to find its inverse, right? But so in general we have not assumed that this is a square matrix. So that way there is no reason to think that an inverse of this matrix exists. But still I may be interested to find what is called a pseudo inverse of X. What is a pseudo inverse? Its usual pseudo inverse is usually denoted by X dagger. It's like saying that if you pre-multiply x by x dagger, then you will get back the identity matrix, right? Identity matrix of the appropriate size. In this case, that being n cross n, right? So this thing is called the sometimes it's called the left pseudo inverse. And then there is the right pseudo inverse also. X naught, sorry, x dagger will be equal to I. In this case, I m cross m, right? So this is the right pseudo inverse. So it turns out that using the concept of SVD, we can find out the left pseudo inverse of any given matrix. So how so? So before that, let me make a claim. The claim is that this quantity x transpose x inverse x transpose, this is the left pseudo inverse of x, right? So if x transpose x is indeed invertible, and if I define it, then you can easily confirm that yes, this kind of a matrix will indeed act as the pseudo inverse of x. That is to say, if I post multiply this by x, that is if I calculate x dagger x, then obviously this is going to be x transpose x whole inverse times x transpose times x, right? Now using the property of associativity, I can put the brackets here so that this becomes x transpose x inverse x transpose x, which is nothing but I of n cross n, right? So if this quantity can be calculated, then yes, it definitely will act as the left pseudo inverse of x. Now the question is, how, from where, or that is given x, how will I find this kind of a quantity? Where will this quantity come from? So let's take the help of SVT. I know that x can be expressed as u sigma v transpose. Now what about x transpose x then? X transpose x. So this we, like yesterday we briefly studied x, looked at x transpose x for the Frobenius norm of x. So x transpose x, x transpose as we discussed yesterday itself is nothing but v sigma transpose u, okay, and multiplied by x, sorry, u transpose, right, multiplied by x, which is u sigma v transpose. Now, because u and v are both orthogonal, so u transpose u has got to be the identity matrix. So what I get is v sigma transpose sigma transpose sigma v transpose. Okay. Now this you can that is, you can actually check out what the sigma transpose sigma is going to be, given that sigma is like something like a diagonal matrix whose which is of this manner, that is all its diagonal elements are maybe there are some extra zeros here, that is if m is greater than n, then this is what sigma looks like, and if m is less than n, then this is what sigma looks like, right? Fine, but the singular values of x are all placed along its diagonals. So these, so the first diagonal element is sigma 1, next is sigma 2, etc., all the way up to sigma r. Similarly here also, from sigma 1 to sigma r. Now then the question arises in either whether it is like this or whether it's like this. If you look at this matrix sigma transpose sigma, what happens to it? So sigma is obviously it's what's the size of sigma? This is an m cross n matrix. So then sigma transpose sigma obviously will have to be n cross n, correct? And what are the diagonal, and you can also convince yourself that the diagonal elements of this matrix is going to be sigma 1 square, sigma 2 square, all the way up to sigma r square, followed by zeros. And the off diagonals are of course going to be zeros. Okay, so you can just convince yourself that this is indeed the case. So this sigma transpose sigma matrix, let me write it as sigma, capital sigma square. Okay, so okay, or if you I mean this is a slight abuse of notation, because sigma transpose sigma is not exactly sigma square. Sigma square basically means like sigma dot sigma, which is I mean sigma into sigma, which is strictly speaking not the case, but by a slight abuse of notation, let me write it like this. This square does not indicate that it's being multiplied by itself. It simply means that it contains the squared of the squares of the singular values here. So I am writing this as V sigma square V transpose. Now you can understand that this matrix now will be like it can be invertible, right? Right, and then and if this is invertible, okay, so first of all, tell me under what conditions this is invertible. This matrix sigma square, I mean sorry, this whole matrix, under what conditions is it invertible, or is it always invertible? What is the condition of a matrix being invertible?
It should have linearly independent rows and columns.
That means what? Correct. So that means what?
It should be non-singular.
Right. Right. Correct. So it's so basically so these are all correct. What all you are saying is all correct. So now, if this thing is non-singular and hence invertible, then I will be able to take it, calculate its inverse as x transpose x inverse, and then you can like let us see what that inverse looks like. This will basically be V sigma square V transpose inverse, right? And noting that V is an orthonormal matrix, and applying like some standard properties, you can actually find out that, or you can actually calculate that this is going to be nothing but sigma square whole inverse, right? So and if sigma square matrix is like this, then what is sigma square inverse matrix going to be? I mean, if sigma square if this is sigma square matrix, that is the diagonal elements are sigma 1 square, sigma 2 square, all the way up to sigma n square. It's an n cross n matrix. So so obviously, if this r is less than n, then we may not be able to do much. I mean, we may not be able to invert it. But assuming that this is like its rank is n, that is sigma 1 square, sigma 2 square, sigma n square, then what will be the inverse of this matrix? What will it look like?
All inverse of singular value.
Basically the reciprocals of the singular values. Yeah, 1 by sigma 1 square, 1 by sigma. It will be another diagonal matrix whose diagonal elements are like this, right? Okay, so so this is what the x transpose x inverse will look like. And then what do we need to do? I after that I need to multiply it, sorry, it by x, by this x transpose. So x transpose inverse, x transpose x inverse has become sigma 2 inverse, sigma square inverse, and then I further multiply it by x transpose. So what is it equal to? X transpose is equal to V sigma U transpose. Okay. So So now, like, if we can, like, with a bit more mathematical jugglery like this, we can, like, we will be able to express this quantity in the following way: sigma transpose sigma whole inverse times sigma transpose into V of ut. So that is like, basically, to get that form, I will have to, like, play a little more games with the sigmas, which I leave it to you as an exercise. I mean, you can see it here itself. So then what? So basically, then what happens to this expression? We have the sigma transpose sigma inverse. We have already calculated that sigma transpose sigma is the sigma square, and the inverse of that I have already calculated, and that further I have to multiply with sigma transpose. And if I multiply that with sigma transpose, so you can, for the paucity of time, I'm not showing all the steps, but you can verify that if you multiply it with sigma transpose, this is what you will get. That is a diagonal matrix with one, I mean, sorry, not a diagonal matrix, an n cross m matrix whose diagonal elements are 1 by sigma 1, 1 by sigma 2, etc., 1 up to 1 by sigma n. Okay? So this is what you will finally get. So if you know, basically, if, once you know the that is given x, if you can do the SVD, that is, you can get u sigma v transpose, then that will enable you to calculate this quantity, which is called which is nothing but the left pseudo inverse of this matrix X. Okay. So even though this is not a square matrix, and so there is no question of calculating its inverse, but at least its pseudo inverse I am able to calculate in this way. Okay. But what is the but what is the necessary or what is the condition which this has to satisfy for this left pseudo inverse to exist? The condition which it must satisfy is that this matrix has to be invertible. That is, this x transpose x, this must be invertible, otherwise we will not be able to proceed. And as we discussed already, when will this x transpose x be invertible? If it is like if all the, as you said, if all the rows and columns are independent of each other, or if its determinant is non-zero, etc. Both of these statements are correct, but it basically means that it has to be a full rank matrix. That is, the rank of x transpose x will have to be equal to n. But what is the rank of this x transpose x? I mean, it obviously it is R, so basically this R has to be equal to n. Okay. So that is why the requirement here for this left pseudo inverse to exist is that the X has to be a full column rank matrix. What is column rank? So column so like the rank of this matrix, as I have said earlier also, it cannot be more than the minimum of m and n. So let us say that m is greater than equal to n. So that is to say the number of columns is n. So a will have to, the rank of a, which is R, will have to be exactly equal to n. If it is any less than n, then this analysis will not go through. If A is any full column rank matrix, we will be able to calculate its pseudo inverse in this way. Okay. Now we'll take a short 5-minute break, after which we will resume one more discussion, that is resume discussion on one more application of SVD. Okay, welcome back. So let's now now let us just move away from what all we have been discussing. So let us consider some data. Okay, so since this is a class on machine learning, sorry, I mean linear algebra for machine learning and AI, so at some point we'll have to deal with data rather than dealing with only symbols. So let us say that this is what our data set looks like. So let us say that it's a very simple data set. I mean, there are only two features, x1 and x2. Okay, and what I have and both of them like take real values only. So x1 also takes real values and x2 also takes only real values. Okay. Now let us say that I have n number of data points, n number of observations, and let's say n equal to 100 or something like that. And by what I mean by observations is that like for every data point, or I am observing its features. Features as in the x1 as well as x2. So I am going to denote my data set in this way: I equal to 1 through n, where xi is basically a vector. It's a two-dimensional vector. Its two elements are xi1 and xi2. Right? So so like this is basically the I is basically, you can assume that it's the observation number, it's a serial number of the observation. xi1 means the x1 component or the x1 feature of the ith observation, and xi2 means it's the ith the second feature of the ith observation. Okay, and since both of them are real numbers, I can plot them like I can plot these observations on these two-dimensional plots like this. Okay, so let us say assume that these are three different data sets. Let's look at this particular data set first of all. So you can see that if I plot the different observations along the on the x1 x2 plane, this is where all my observations lie. I mean, I have written n equal to 100. Obviously, I have not drawn all the 100 points here, but I'm presenting to you only maybe a subset of about 10 points or so. Okay, so since this is one data set, this is a second data set, and this is the third data set. Now suppose so this is now suppose whatever algorithms or I am going to, or whatever analysis I am going to do on it, I need to use like both, like I need to use these two features, the feature x1 and the feature x2. But suppose I tell you that like my whatever algorithm I am going to use, that has some computation cost, and that cost is maybe something like say order of say kd, or maybe order of k to like kd square, etc., where what is d is basically the dimensionality of the data. So what does that mean? That means the higher the number of dimensions which I have, the more complex my computations are going to be. Okay, so that means what? So this is sometimes known as the curse of dimensionality problem. if the data is, I mean to say, the dimensionality in this case is what? Then every dimension of this vector is a new feature, and we know, we can understand theoretically or like just intuitively, that more are the number of features, the better we will be able to express the data. That is, say for example, what I am doing is I am solving a face recognition problem. That is, these the observations which I have got, these are basically representations of human faces. Now of course these features are like different attributes of a human face attributes. So like for example, you can like consider different attributes of the faces. Most importantly, maybe with, is it a is the complexion, is it fair or is it dark or is it medium, or like does it have spects or does it not have spects, or various like that, like does it have a lot of hair or is it bald headed, like what is the color of the eyebrows, what is the color of the pupil, etc. Like many attributes can be defined on the human faces. And obviously it should be intuitively clear that more the number of attributes, the better we will be able to represent the person's face. In general, that's true. The using a high number of features gives more expressive power to the representation. But there is a curse also. The curse is that the more you increase the number of features or the dimensionality of the data, the more difficult the computation becomes. So I do not actually want to keep on increasing all the attributes, but rather I want to select the more important attributes. That is to say, if I have lots of attributes, I will try to keep the ones which are more important, and which I will try to give away those attributes which are less important. Okay. Now let us consider the simple human face recognition problem. So let us say that I have three different attributes for the human face. One is number of eyes, the second is color of pupil, and the third one is presence or absence of spects. Now, if these are the three attributes that are available, like can you say intuitively whether all of them are equally important or not for the purpose of face recognition? Or if not, which features are important and which are not? Yes, anyone? To answer this question, you do not need to know any machine learning or linear algebra or anything.
So the number of eyes feature seems to be like not useful.
Yeah, and why so?
Because in general everyone has two eyes.
Right. Because for all the observations you will have, the number of eyes will probably be almost equal to. So if there is one feature for which there is not much variation across the observations, then it's probably not an important feature, right? So if you look at this particular dataset number 1, here can you say like here if there are two features, obviously x1 and x2. So here can you say which feature is important and which is not?
X2 is important, X1 is not.
Right, because x1, it's not that all the features, all the observations have exactly same value of x1, but you can understand that the values of x1 are lying in the small range, while the values of x2 seem to be quite widely separated. In this data set, it's the reverse, right? That is, it seems x1 has a lot of diversity, but x2 is like, it seems to be more or less constant. So in this case, I will say that x2 is important, x1 in this case I will say x1 is important. So if like in this case, if I have to run an algorithm like which is quite costly in terms of its dimensionality, I will probably drop the x1 dimension altogether and focus only on x2. In this case, I will do the reverse thing. What about this case? So can you, like in this case, can you do you have any observations about this data set? Suppose I want to that is x1 and x2. I mean both x1 that is I cannot say that either x1 or x2 has low variance. Both of them seem to be having near equal variance. But still, suppose I want to that is express the that is I want to I do not want two-dimensional data. I want only one-dimensional data. So in that case, what can I do? Can you have any suggestion or observation related to that? So I am sure you are familiar with the concept of change of basis, right? You would have studied this sometime in your +2 itself while studying for JEE, right? So suppose instead of using a basis, using this basis or defined by x1 and x2, suppose I define a different basis. Suppose this basis, that is instead of calling this as x1, I call this as x1 prime and I shift x2 to x2 prime. Okay. So now you can understand that along the dimension of x2 prime there is hardly any variation, and all the variation seems to be along x1 prime, right? So that is to say, if I project the data in like along a different dimension and I find that the variance of data along that dimension is quite high, then I may choose that dimension, leaving out the other dimensions. Right? So that is, if I can somehow represent the data in terms of x1, like in terms of its x1 prime coordinates rather than x1 or x2 coordinates, then I can actually forget the x2 prime component and use only x1 prime as that is only a single number to represent the data, right? So like basically by doing this system of change of basis, I am able to significantly reduce the dimensionality of the data from 2 to 1. Okay? But the question is, from where I will get x1 prime? I mean, x1, x2 basis is there. I can shift it in various ways. Like this is one possible, like I can also get this one, or maybe I can get this one. Right, I can define x1 prime, x2 prime in various ways. What is the way in which I want or what x1 prime or what x2 prime should I choose? So the thing to be noted here is that what is the speciality of this particular x1 prime as opposed to say this one. Okay, so I am giving you two possible choices of x1 prime, either this line which I am calling as let's say w1, or this line which I am calling as say w2. So why will I choose w? That is, if I have to express this data in terms of one dimension, why will I choose w1 instead of w2? Any idea?
Sir, the sum of squares of perpendiculars from each data point to one x1 prime, that is w1,
Yeah.
will be less than w2.
Right. So
Like
so what?
probably
So
it will be
what?
the minimum.
So what? So why is that? So what is great about that? What you said is definitely correct. Definitely that is an important reason. So but what so why is that important?
So W1 represents the data more accurately as since the sum of residuals is less.
Right. That's a good answer. It's like saying that if we project the data onto W1, then the projections will be quite close to the original data itself. as you were saying earlier, that is the sum of the squares of the perpendiculars will be less. That means what? That basically those sum of the squares of the perpendiculars actually represent nothing but the error of projection or error of approximation. What I am doing essentially is I am doing an approximation. In this case also I did an approximation by basically I forgot all the x1 values and I was just looking at only the x2 values. The x2 values being something like this. In this case also I did the same thing. I'm doing some kind of an approximation. So here also I am doing an approximation, but the approximation I have to do anyway, but I will choose that approximation where the approximated data is as close to the original data as possible. In other words, the least square is minimized. Very good. Any other reason apart, maybe the same thing said in a different way, but any other reason for choosing this thing, this W1 over W2? So just to give you a hint, in this case, we decided to drop this number of i's because it's nearly constant. In these two cases also, in this case, I decided to drop x1 because the values here are nearly constant. Now, based on this notion of being nearly constant or not, can you give some other justification of choosing W1 over W2?
Dimensionality will be reduced.
Dimensionality is anyway reduced. Whether you are going for W1 or W2, dimensionality will always be reduced from 2 to 1. What else? Whenever we are talking about something like some value, some feature being constant or nearly constant, what mathematical or statistical quantity are we talking about, or are we implicitly talking about?
The variance of
Variance. Right, that is the answer I was looking for. Very good. Variance. That is what I really want to do is I want to choose that dimension along which the variance is high, and I do not want that dimension or those dimensions along which the variance is low. So here you can understand that if, like in this case, if the values if the feature is constant, then it has no variation, so it's useless. In this case also the variation is very low, so we can say it has low variance, while in this case it has got high variance. Similarly, if we project the data, all my observations along on W2, we will get some variance, but it seems like if we project the data along W1, we will get a much higher variance, right? So two things I have. So basically, whenever I am trying to reduce the dimensionality by projecting the data on a different space, or rather by taking a change of basis, I am interested in doing two things. One is minimize error of approximation, and the second thing is maximize the variance. Both are things which are useful for me for this purpose. So one is a minimization, the other is a maximization. Now let us first solve a simple problem like in two dimensions. Then we will gradually generalize it to higher dimensions. So let us again say that let's say that this same data set we are dealing with, x1, x2, the data are arranged like this. And what we want is to find some vector which is like w. So I can call this x1 as a vector, like x1 vector. Similarly, this I can call as the x2 vector. I mean, denoted by their unit vectors, right? Like you can denote it by this. The unit vector of x1 is 1 0. The unit vector of x2 is 0 1, etc. Now w is also a vector, and I want to find that is I want to find what vector that is. So basically what I am doing here is that I am projecting the data onto this vector. So if there is any particular like this particular observation, let me call it as xi. Okay, this is the ith observation. It, as I said earlier, it's a two-dimensional thing. It contains xi1, xi2. It's a two-dimensional vector. Now what I am doing, I am projecting this this observation onto this W. So the definition of projection in this case is defined as follows: X transpose W, or the dot product of X with W into W. Okay, or you have, I mean, of course, you can write it also as W transpose X W. Okay, fine. So similar, I mean, not X, Xi. So basically what you are doing, like you are so the initially you had got the like you had xi, its project, after you project it onto W, its projection becomes what? Its projection basically becomes just this length along the direction of W. So you like why is that so? That's because whenever I am talking, like you consider the geometry of the thing first. So let's say this is xi, this vector, and let's say this is W. And so when I am talking about the dot product between this, W may be an unit vector also. Now that means what? That means the L2 norm of W is equal to 1. Now when I am talking about this quantity xi dot W, what does it mean? Like as you would have studied in physics for your class 2, xi dot W basically means the magnitude of xi times the magnitude of W times what? Right? I'm sure you had studied this in physics for or something for your JE. Right?
Cos
Cos
of
of the
theta
angle
between
between
xi
W
and
and
y.
X.
Cos of theta, where theta is the angle between this angle basically. Right? Correct? Now W, as I have already said, is unitary. So its magnitude is going to be 1. So so this is xi transpose W is just basically the magnitude of xi, which is the length of this line, times cos theta, where theta is this angle. So what do I, so basically that means what? That means I drop a perpendicular like this, and and I calculate. So if I calculate the this this length times cos theta, that is nothing but this length, right? So this length times W. What is W? W is the unit vector in this direction, right? So basically what I have, after doing that is after carrying out this operation, what I got is like a vector along the direction of W whose length is precisely this much. Fine. So like initially my observation was xi, which is a two-dimensional vector. Now it has become this thing. This is what it has become: W transpose xi times W. Fine. So similarly, all the data which I have, I like x1, x2 up to xn. I just project onto the same W in the same way. So that x1 becomes W transpose x1 times W, x2 becomes that thing, and similarly xn also becomes a W transpose xn W. Fine. Now what I am interested in? I am interested in variance. What is, so variance, let me denote variance by C. Okay, So now variance of what am I interested in? I am interested in, so since they are all of them are in the same direction W, this like basically it's now a matter of the magnitudes. So what is the so basically I like you can say that I have lots of numbers like this, W1 transpose X1, W2 transpose X2, etc. And since they are dot products, all of these are basically scalars, right? It's a scalar. I can sometimes I may call this as the loading of X on W. So basically, like I have got all these kinds of loadings. So now what I want to do, I want to choose such a C for which these loadings, the variance of these loadings is going to be as high as possible. So first of all, so let me write what is the expression for these loadings. So what is the expression for variance? We all know. So like so in general, we know the expression for variance is as follows: 1 minus n summation any xi squares minus 1 by n xi whole squares, right? Mean of squares minus square of mean. This is the definition of variance. So in this case also I'm going to do the same thing, except for xi I am going to put in w transpose xi. So now let me do one okay, fine, leave it. Let me do it, write it in this way. Summation I equal to 1 through n summation of I equal to 1 through n xi, instead of xi square I will write w transpose xi whole square minus 1 by n w transpose xi the whole thing squared, correct? In other words, I can also do a bit more of mathematical jugglery, and I can get it like this. W transpose xi minus x bar whole square. What is x bar? X bar is the mean of the mean vector, basically the mean of all the observations. Okay. Now I will again do a bit of more trickery. So notice that this is a scalar quantity whose square I have taken. Let me write this in the following way. W transpose xi bar times xi bar, sorry, xi minus x bar transpose w. Fine. Are you like, do you agree that this, like what I have, this new expression is nothing but the same as this expression? Right? It just follows from the fact that a dot b is equal to b dot a. So I was basically trying to do a transpose b whole square, that I wrote as a transpose b whole square means a transpose b times a transpose b, which in turn means a transpose b b transpose a. The same thing I have done here also. But in doing that, something strange has happened. What is xi? So to remember, just to remind you, w is basically a two-dimensional vector, right? This w basically means the unit vector around this direction. So it's a two-dimensional thing, 2 cross 1. Xi is also 2 cross 1, like it's a two-dimensional thing. So this is basically one. After I take W transpose, this W becomes 1 cross 2, just like this W is 2 cross 1. And this Xi minus X bar, this is what? This is 2 cross 1. And Xi minus X bar transpose is then 1 cross 2. So now, if I apply the principle of associativity here, right? So what is this? This is 2 cross 1 times 1 cross 2. That means what? We know by matrix multiplication that if I multiply 2 cross 1 by 1 cross 2, what I will get is 2 cross 2, which is a matrix. So till now we had been dealing with vectors and scalar, but suddenly out of nowhere I have got a matrix. I have got a matrix which I am denoting in this particular way. Okay. So let me refresh this. So the expression which I have got, the variance, is equal to 1 by n summation over I equal to 1 through n W transpose Xi minus X bar Xi minus X bar transpose W. Now let me bring this summation inside, that is this W transpose W, this is independent of the summation, so let me take it inside and let me write it as W transpose 1 by n I equal to 1 through n Xi minus X bar Xi minus X bar transpose whole thing times W. So, and as you can understand, this whole thing I can call it as a matrix C, which is 2 cross 2. Okay, and this matrix has a particular name. I call it as the sample covariance matrix of X. What is X? X is basically my data matrix, where all the like the observations, say x1, x2, etc., are the columns of this matrix. Okay. So C 2 cross 2. So like as you can understand that this X, this is actually a 2 cross n matrix. Like that, like its two rows are basically the two features which we are considering, x1 and x2, and it's like n. So the columns basically are the observations. So the columns are the observations, and the rows are the features or attributes. Okay. So now what like, so the variance is given by W transpose C W, such that what we know about W we know that it's an unitary vector, that is its norm has to be equal to 1. This is what we know about W. And what else I know? I want to choose W such that this variance is maximized. That's what I wanted, right? I wanted to choose that W. I wanted to project the data along that direction for which this variance is going to be as high as possible. So basically the W, I can now write it as an argmax is the W, or if I may call it as W hat. W hat is basically equal to argmax W transpose CW such that this condition is satisfied. So now what I have to do is I have to solve a particular optimization problem. So this is a maximization problem and this is a constraint. So basically what I have got is it's a constraint maximization problem. So the way to solve this constraint maximization problem, so by the way, do any of you know or have any idea about how we can solve this constraint of maximization problem? Have any of you seen this in any other subject? Have you ever come across, say, Lagrange multipliers?
Yes, sir.
So using Lagrange multipliers, then what can I do now? Okay, in case you don't remember, I will tell you, I define my new objective function in the following way. So this is, first of all, W transpose CW is the quantity which I want to maximize. Then I have to bring in the constraints. The constraints I express in a particular form and I add here. Add it with my objective function to get what is sometimes called the augmented objective function. Now instead of calling it, if the L2 norm is 1, then obviously the L2 norm square will also be 1, or rather if the L2 norm square is 1, then the L2 norm will also have to be 1. So I just put in a square here. Why? Because of mathematically it will be simpler. L2 norm square means what? This basically means W transpose W. L2 norm, if I went for just L2 norm, then I would have to put a square root of that. Now square roots are difficult to handle, so I don't want to go into all that. So I just put the square. That does not change the meaning of the problem in any way. Now what happens then? Then basically I have got this problem, W transpose CW plus lambda into 1 minus W transpose W. Okay. Now what is the what is lambda? Lambda is the Lagrange multiplier. So and this is my augmented objective function. So what do I want to do with this objective function? I want to maximize it. So if I want to maximize something, then what do I usually do? I usually take its derivative with respect to 0 and then solve an equation. So in this case also let me do the same thing. The only difference is that I am trying to, there are two unknowns here, W and lambda. C is not unknown. C, as like if I have my X, then I can get C. So C is not an unknown, but lambda and W are unknown. So let me write this in terms of W. So this is equal. So now what I have to do is I have to do basically what they call as a vector differentiation. So I am not sure if all of you know how to do vector differentiation, but it's not necessary either. So in this case, the rule is that WC with respect to W is nothing but twice is another vector which is in like this, twice CW, twice CW. And then so you can check that C is a 2 cross 2 matrix, W is a 2 cross 1 vector. So if I multiply them, I will get a 2 cross 1 vector. And then here also there is W. So so here I get minus lambda twice W. The same formula I am applying once again. D of W transpose W with respect to W is nothing but twice W. So I write here as twice W. This is equal to 0. Fine. So CW is equal to lambda W. This is what I get. Fine. But I also have to do something more. I have to that is of course that is, so basically I want to solve for W and lambda, because these are my unknowns. But I have got this relation CW is equal to lambda W. And once I solve, so okay, so as soon as you see CW equal to lambda W, what does this equation remind you of? What do you think W and lambda are?
Eigenvalues and eigenvectors.
Right, exactly. So lambda and W are the eigenvalue, are like any eigenvalue and any eigenvector of C will solve this. So this is basically an eigen problem. But then again, C. Okay. First of all, does the before answer ask is talking about eigenvalue and eigenvectors, you need to ask yourself: does C have eigenvalues and eigenvectors? I mean, not all matrices can be eigen decomposed, right? So is C is defined in this way. Now, can C be eigen decomposed? So we will understand later that yes, like if C is defined in this way, then it is necessarily what they call as positive semi-definite. Positive semi-definite. So yes, it can be eigen decomposed. So, but now the question is, C is basically a 2 cross 2 matrix. So it will have 2 eigenvalues and 2 eigenvectors. In general, if instead of 2, if I consider d-dimensional vectors, so this C will be a d cross d matrix. So out of so many eigenvalues and eigenvectors, which is the one which I should choose? Okay, so note that what I am really interested is the variance which I am interested in is W transpose CW, right? And now what is W transpose? What is W transpose C? W transpose C obviously has to be, if I multiply both sides by W transpose, if I multiply both sides by W transpose, then what I will get is nothing but lambda itself. So lambda, the eigenvalue, is my variance, is the variance. But what do I want the variance to be? I want the variance to be as high as possible. So accordingly, I want to choose that eigenvalue which is as large as possible. So although C has many, I mean it can have d eigenvalues and d eigenvectors, I will choose that eigenvalue which is the largest. So basically lambda is then the largest eigenvalue of C. And what is W? W is the eigenvector corresponding to the largest eigenvalue. Right, so this is the what is known as the principal component analysis. So what is the principal component analysis? What is it saying? It's saying that lambda is my largest eigenvalue of C, EV of C, and W is the corresponding eigenvector. Okay, and this W is also sometimes called as the first principal component of X. What is X? X is my data matrix. Okay, so this kind of analysis is known as principal value and principal component analysis. So just before I end the class today, just let me show one more thing. So what we are talking about is the C matrix whose eigenvalues and eigenvectors we wanted to calculate, right? CW is equal to lambda W. This is a problem which we are interested in, where N I called as the was defined as this particular way. Sorry, I mean C was defined in this particular way. Xi minus x bar times xi minus x bar whole transpose. Now let us define something known as x tilde. Okay, x tilde is basically x minus x bar. What is x? X is the full data matrix, which is of the size 2 cross n. In this case 2 is the number of attributes, so I can I can just generalize it to t cross n. And what is x bar? X bar is the mean vector. That is, x bar is nothing but n xi. Okay, so so here you may ask that x I have said is a matrix and x bar I have said is a vector. So how can a vector be subtracted from a matrix? Well, x bar is basically such a matrix where every column of it is x bar is equal to this quantity. So this is also an n cross d matrix with identical columns, that identical value being equal to this thing. So this is d cross n, this is also d cross n, and obviously x tilde will also have to be d cross n. Now x tilde is I have defined as in this way. So basically, sorry, C I can define as x tilde times x tilde transpose. I mean the factor, this factor of 1 by n will be there, that you can ignore. And so this is what is the C will become if I express x tilde in this way. Okay, so this is this I leave it to as an exercise for you to verify. Okay. Now what I am interested in is finding the eigenvalues and eigenvectors of C. So how to get that? So for that, let us consider x tilde as the data matrix, and let us, since this is d cross n matrix, but since it is any matrix, I can eigen decompose it always in this way. Let me say u d v transpose in the usual way. Now what is being asked for? I am being asked for x tilde transpose. So this becomes equal to u d v transpose times the transpose of this, which is v d transpose u transpose. Now v transpose v is equal to I, as we have seen so many times earlier. So this basically becomes equal to u d transpose, which we can express as d square times u transpose. Okay, right? Of course that factor of 1 by n is also there. So now what so when we are talking about the largest eigenvalue of C, so by looking at this form you can understand that the largest the eigenvalues of this C is nothing but the squared the squared singular values of x tilde, right? That's the way it looks like. So basically the sigma, so this d square, this matrix is nothing but like the same matrix as we are discussing before the break. Sigma 1 square, sigma 2 square, all the way up to sigma d square, right? And then sigma d square, and it's so it's these values which are actually going to be the eigenvalues of this C, right? So these are the eigenvectors of C, and these sigmas, these squared sigmas, these are the eigenvalues of C. But what are these sigmas? These are nothing but the principal like the singular values of x tilde.
So the factor of 1 by n should also come out.
The factor of 1 by n is also there. So let us say that let's say that I absorb this factor of 1 by n into this matrix by multiplying all of them by root n. Okay, so sorry, by n here. I absorb it here. So it's basically this sigma 1 square. It's like so I am absorb like so if I know the singular values of x tilde, I can just that is square them and divide them by n, and they become the eigenvalues of C. That is exactly what I want. So and what are the w's then? The w is the eigenvectors of C, but as it turns out that these are like nothing but the left singular vectors of x tilde. Okay, so basically when I am trying to maximize the variance, this delta then is the largest or the first SV of x tilde squared and divided by n. And similarly, this W is nothing but the first left singular vector of x tilde. Fine. So this is the way, like, so using if we know that is if we know SVD, SVD can be calculated for any matrix x tilde regardless of what its dimensions, size is. So I just calculate its singular vectors and singular the lambda is actually not that important. The important thing really is W. And so the W's are basically just the leftmost singular vector of x tilde. So so this kind of analysis is known as the principal component analysis, and that these left singular vectors of the diagonal the data matrix, these are called the principal components of the data. So these U, they basically U basically U1, U2 all the way up to some UM are there. So sorry, in this case I'm calling it N, UN are there. So these are basically the principal components of, I call it as X. Okay. So a little more of this we'll discuss in the next class. So we are past time, so we'll end the class here. Thank you.